Alright, just gonna make sure everything's set up properly. Open a little Word doc. Alright, let's open a new one. Get rid of this. Alright, 10:25 review session starting at 4 p.m. Alright. Ooga booga. Let's get some music while we wait. Just gonna listen to some. Oh, that's not happening. Alright, well, you can imagine some music. I'll just do this. Alright. Hope everyone's having a good Sunday. Drinking coffee, drinking water, doing whatever it is to get you through your Sunday, doing homework, hopefully, studying, whatever. Alright. Let me go ahead and pull up the Zoom thing. This is my technique for sharing my iPad screen. So, yeah. Alright, check it out. Start that in a moment. Got this going. Alright. I'm gonna give it a few more minutes. Start right at 4. We'll just work through some problems. Alright. I'm gonna get some light in here. Let me see how this video looks. With a light. Alright. Looks about the same to me. I don't know. Oh yeah, sorry for this mess of a... There we go. Let's get back to this. Alright. This thing is live. This thing is live, right? Yeah, we're live. Public. I don't know. We'll be at. Alright, we'll be starting in 30 seconds. Basically for today, I don't think I received any problems, and that's fine. I have plenty of problems to run through. I'm basically just going to run through 18 practice problems to mimic what the exam 1 will be. 18 random questions from quiz 2 and quiz 3. Picked some good variety. So it's about 4 o'clock. Let's get started. Hokie dokie. Welcome to the exam 1 review for 10:25. We're just going to run through 18 different types of problems in hopefully about an hour. I'm going to try to keep it real concise with basically how I would approach everything. And for any of them, if you want longer explanations, go ahead and just watch the video for these problems, because these are all the problems that I have longer videos for. So I'm just gonna work it out basically how I would approach it while explaining things along the way, so you're not just in the dark, you know what I mean? All right, let's get started. Number 1. Which of the following graphs best represents the ratio of surface area to volume, or SA over V? So in this problem, we're given V and SA, and the goal is to identify which of these graphs correctly represents the ratio SA over V over time values from 0 to 4. And so my approach is picking t equals 4, and what I do is identify the volume value at t equals 4, and I identify the surface area value at t equals 4. And so I'm going to set up this ratio. So from the surface area graph, we see that we have a y value of about 4 at t equals 4, and then we look at the volume graph, and at about t equals 4, we have a y value of about 40. So that means the volume is about 40. And so if we reduce this fraction, we get about 1/10, or we get 1/10. And then from there, what we do is look at these options here. Again, these are the surface area over volume ratio graphs. And because we found the surface area to volume ratio at t equals 4, what we'll do is just find which one of these graphs has a y value of 1/10 at t equals 4, because the y values on these graphs represent ratios of surface area over volume. So let's waste no more time. At t equals 4, down here we have a y value. So on graph 1, we have a y value of like -40 at t equals 4, so that's not it. Again, we're looking for 1/10. Graph 2, t equals 4, the y value is like +40, can't be that one. And graph 3, we have a y value of something very small, very close to 0. So that's likely our best bet, because that y value here is approximately 1/10, especially if we look at 4 and we realize the y value at t equals 4 on graph 4 is about 10. So it's definitely not 1/10. So 3 is our best option. If we break out the eraser, we see that 3 is our answer. All right, let's keep it pushing. Number 2, and I'm hoping the chat comes through on here. So if you happen to have any questions, I don't think anyone's even viewing this right now, it's fine. But if you have any questions, here, let's see if I can sign into chat. Yeah, that's all right. If you have any questions, try to let me know in the chat, and yeah, so, let's just keep going through it. I don't think anyone's in here. Hopefully someone can benefit from just watching this later. I'm not sweating it. Let's go on. Number 2. In this problem, they give us the function f of x on the graph, and they ask about where it's increasing or decreasing and over what intervals. So basically, we're just going to go through each of these statements and identify which ones are true, which ones are false, eliminating which ones are false along the way. So option A. They say neither strictly increasing nor decreasing over 5 to 6. So over 5 to 6, they're talking x values. So from 5 to 6, that is actually strictly decreasing. The y values are decreasing from left to right. Therefore, it's decreasing over 5 to 6. So to say it's neither strictly increasing nor decreasing is false. All right, so that eliminates all of option A. Let's move on to B. They say increasing over 2 to 4. Increasing 2 to 4 is correct. Neither over 7 to 8. So from 7, now that's kind of a tricky one, but to be honest, I would say that's strictly increasing rather than neither strictly increasing or decreasing. So I think because that's wrong, I'm not feeling B. Let's look at option C. They start with increasing over 7 to 8. And again, that's what we just said, so I think that is a true statement. Let's go on to this one. Decreasing over 5 to 6. We did say that, I think, in the very first one. That checks out. And then the last one, increasing over 9 to 10. Okay, well, from 9 to 10, that's decreasing. So, can't be that. We were so close. And then... okay, well, before I cross that all out, notice that these first two statements, I believe, are correct just based on option C. So we can kind of like use that prior information. And then they say, the last one on D, neither increasing nor decreasing over 8 to 9. So let's get rid of this, from 8 to 9, we're looking at a function that is increasing all the way just about up until t equals 9 or x equals 9, and then it just barely starts to decrease right before it hits 9. So that is our answer. That is our correct answer. That's pretty much it. Let's keep it rolling. Number 3. They say, suppose you know that the mass of the bacteria culture grows exponentially. All right, perfect. Right away, they're telling us the bacteria culture grows exponentially, which means the bacteria mass function that we are trying to identify from this chart will be something of an exponential form. So all these linear functions that you see just can't be the answer, because bacteria mass should be an exponential function. So just off that first information, we can eliminate the majority of the answers. And then they say using log plots to estimates the data in the chart. So basically, what we're given here, we're given 2 time values, and we're given 2 basically y values. Whenever in this section, there's multiple problems that deal with it. Whenever they take the natural log of bacteria mass, that result is y values that create a linear function. And so we mentioned that bacteria mass, or the function we're looking for, is an exponential function. So on a graph, it would look like this. But when you take the natural log of that graph, or of those values that create that graph, it actually transforms that exponential curve into a linear curve. Now, why is this important? Well, if they're giving us the ln values in this chart, they're basically giving us values that create a line, 2 points that create a line. And so if we have 2 points that create a line, we can find the slope between those 2 points to give us information about that linear function. And really, that'll lead us to canceling or eliminating more options. So let's just go ahead and find the slope between these 2 points. So again, the ln bacteria mass values are like your y values. So y2 minus y1 would look like this. And then we divide by x2 minus x1. And just because I want to be efficient here, I'm just going to use my phone calculator, just making sure to do the numerator calculation first, and then divide by 5 minus 3, or just divide by 2, and we get 0.9. So again, this was just the regular slope between these 2 ordered pairs in the chart, and this 0.9 should correspond to either G or C, because 0.9 is the value that's in the exponent. And so we can eliminate those, and now we're trying to just identify which one of these is correct. So here's the approach. If we know that plugging in 3 to, basically we're just going to plug in 3 to this option and to this option. This will give us the bacteria mass values for each of these options at t equals 3. Then what we'll do is take the natural log of both those values. Whichever one of those natural log values matches the one in the chart will be our correct answer. Because in the chart, they don't have just the bacteria mass value, they have the natural log of the bacteria mass value. So let's plug in t equals 3 to both of these. Again, I'm just going to do it on my phone, but we're just plugging in t equals 3 to these 2 functions, c and g. So 0.9, we'll do 0.9 times 3, and then that's our exponent, and then I'll do e to the x, so e to the 2.7, and then times 90. So when I did this, I'll do option C right here. This is for the bacteria mass value. I got 1339. I'll just leave it at that. And then when we take the natural log of 1339, natural log of that result, we get about 7.19. Really like 7.2 if we round. And so what we would be looking for is 7.2 in this chart for the t value of 3. Because we plugged in t equals 3 to the bacteria mass, we got that bacteria mass value, then we took the natural log value of it. And so because 7.2 does not match 9.5, then it really only leaves option G. And so just to demonstrate, when we plug in t equals 3 to the function in option G, we will get, so I'm plugging in my phone again, 0.9 times 3, and then we'll do e to the x, and then we'll do times 990. And that'll give us a huge number. So the bacteria mass value is about 14,730, and that looks ridiculous, but again, you take the natural log of that result. And what we're looking for is, or what we get, I guess, is 9.59. I mean, yeah, I'll round it how they do. So 3 decimal places, it's 9.598. It was like 977 altogether. Anyway, this value matches the value in the chart. Therefore, G is our best choice. G is our answer. All right, let's keep it pushing. Number 4. All right, I put these problems back to back just because they're similar. Let's check it out. It's actually a very similar approach, if I'm not mistaken. So let's jump right into it. If you notice, just like in number 3, what we're given here are the natural log of y values. So natural log of the bacteria mass values, it's kind of similar. Yeah, I guess they don't say bacteria mass. Anyway, natural log of y values, where the y values were originally an exponential function, will create a linear function out of those exponential values. So basically, we're given a line here, and we're given 2 ordered pairs on that line, very similarly to how we were given 2 ordered pairs in this chart with ln of y values, or ln of bacteria mass values. So first step is actually this same step in this one. So what we're going to do is, with these ordered pairs here, we're going to find the slope between them. Slope between these 2 points. So we do y2 minus y1 and divide by x2 minus x1, or t2 minus t1. I will calculate this on my phone, just making sure to calculate the numerator first. 0.435. There we go. And then divide by 3.9 minus 0.3, or just divide by 3.6. And if I've done that right, I got a slope between these 2 points of 0.21. Again, 0.21 should be the exponent of the e term, and it shouldn't be negative like in option C, and none of the others match 0.21. So if I'm just doing this efficiently, I would just choose B based on that slope. Again, if you want more of a breakdown on these, I have videos for all these. These are all the same ones in the longer video, so I'm just going to keep it pushing. I'm just going to do it like I would on a regular test. So let's keep going. Number 5. In this one, they give us 3 statements. First, about the concavity, and then something about the rate of change being positive or negative. And so what I usually start with is the concavity ones, because usually these first 2 statements, usually you don't have to actually look at these intervals, because what they're describing is like how the graph starts and how it ends from left to right. So they're basically saying on the left, it should be a concave down curve, and then as it moves towards the right, it will change from concave down to concave up. And so let's look at these graphs. Which one starts concave down and ends up concave up? So again, concave down is something of this behavior, and then concave up is something of this behavior. So any like pieces of these concave up or concave down curves is what we're looking for, because obviously we don't see like a full concave up or concave down curve on these graphs. So looking at option A, that one starts concave down and switches to concave up, which is the idea. That's what we're looking for. So A is a potential option. B, not so much. That starts concave up at its leftmost point. So B is out of here. And then C, it's very subtle, but you can see it curving up like this, which actually leads to a concave up curve off the start. And so C is out of here. And then D, kind of the same way, but just the opposite. So it actually starts down, or in that concave down sort of behavior, and does in fact switch to concave up. So we're between either A or D. And then we move to that third statement. They say the rate of change is negative for x values less than -2. Really, it should just be negative just about the entire time, except for like right in the middle. No need to worry about that. But basically just ignore this. And what we're looking for is the graph between A or D that has a negative rate of change. Again, rate of change is just a phrase for slope. So, which one of these graphs has a negative slope? That would be A. So a negative slope meaning it's decreasing from left to right. All right. And so A is our answer. All right, let's keep it pushing. Number 6. In this problem, they basically give us a bunch of graphs that all appear to be linear functions, but as you notice, they have different scales on the y-axis. And the goal is to identify which of these graphs actually represents a linear function. And the most defining feature about a linear function or a graph of a line is that it has a constant slope the entire time. So we'll basically be finding the slope between points 1 and 2, and then we'll find the slope between points 2 and 3, and then we'll see if those two slopes are equal to one another. And that'll justify that the entire line has a constant slope, at least for the duration of the graph that they show us. And so how I would approach this, instead of having to deal with like y2 minus y1 over x2 minus x1, I'm still kind of doing that, but I'll think about it more in terms of rise over run. And so getting a closer glimpse at this first graph here, the rise, so again, we're finding the slopes between these first 2 points first. So the rise from 7 to 10 is 3, and the run is from 6 to 8. So that's a difference of 2. And then if we find these slopes, or find the slope between the second and third points, we are rising from 10 to 12, so that's a rise of 2, and a run, I'll do it like this, a run from 8 to 9, which is a run of 1. So again, what we're checking for is, does 3 halves equal 2 over 1? So does 1.5 equal 2? No, it does not. All right, so that's what we're looking for. That's why we can eliminate option A, and we're just looking for the one that has 2 slopes that are equal. So let's keep it going. Let's speed it up a little bit. The rise here is 10 from 27 to 37, and the run is 2 from 6 to 8. So 10 over 2 equals 5. And then if we rise here, we're going up 6. And then we run from 8 to 9, so 1. So does 5 equal 6? It does not. B's out of here. Option C. We rise 6, and then we run 2 from 6 to 8. And so that's a slope of 3. And then from here, we rise 3, and we run 1 from 8 to 9. So 3 over 1. Does 3 equal 3? Yes, it does. So I would say C is our answer. All right, let's keep it pushing. Number 7. In this problem, they give us a chart with day and biomass values, and they really just give us 3 statements regarding the, what are they asking about? The rates of change over the stages. That's right, okay. So for this problem, what I would recommend is sort of just making another chart. All right, making another chart with 1, 2, and 3 stages. And for each of these stages, what we want really are the rates of change between the consecutive intervals in the given chart. So what I mean is stage 1 is going to represent the rate of change from 14 to 44. And stage 2 will represent the rate of change from 44 to 48. Stage 3, 48 to 50. So what we need to do is find the slope between these points, between these points, and between these points. And those will become the rates of change in stages 1, 2, and 3 respectively. And then once we have those kind of like laid out in front of us and taken care of, we can just reference that while we're analyzing the statements. So, excuse me. what I'm doing first is finding the slope between these 2 points where the biomass values are like your y values. So I'm going to find the difference in 149.2 minus 77.2, so y2 minus y1, and then I'm going to divide it by the difference in the days. So 44 minus 14, what is that? That's 30, so divided by 30 will give us 2.4, and so 2.4 is the rate of change between 14 and 44, therefore the rate of change for stage 1. So now I find the slope between these 2 points, and that'll be for stage 2. All right, so 170.8 minus 149.2. That gives us 21.6, and we divide that by the difference in days. So 48 minus 44 is 4. So I divide by 4, and I get 5.4. And for stage 3, we get 172 minus 170.8, 1.2. And then we divide by the difference in days, so that's just 2. So we get 0.6, and we have all our rates of change. So now we look at the statement. Statement 1. The biomass increased most rapidly during stage 1. So that is false because it increased most rapidly during stage 2 because the rate of change is larger. Number 2. During stage 2, the biomass increased at a faster rate than during stage 1. That is true because at stage 2 it was 5.4 and stage 1 it was 2.4. So it increased at a faster rate during stage 2 than in stage 1. Number 3, during stage 3, the biomass increased at a slower rate than during stage 2. That is also correct because in stage 3, we had our slowest rate of change of 0.6, and that is much slower than 5.4. So it looks like 2 and 3 are correct. We choose G and keep it rolling. Number 8, I thought I'd just throw this in there. You will get a mix of, moderate to hard problems, but also some easy problems in there. So here's an easy problem. Or if it's not easy for you right now, let's talk about why it's easy. All we need to do is, starting from this equation, I'll go ahead and just rewrite it here. Really, you can kind of pick up on like the pattern with finding the answer to this one, but how you would do it, I guess algebraically, is aim to eliminate the e term from the equation, and we would do that by taking the ln, or the natural log of both sides, and then from there ln and e will cancel and leave you with just 7x plus 8 on one side of the equation, and then just ln of 14, or natural log of 14, on the right side. And then really all they do is sort of flip-flop them. I don't think that's anything like too it's they're not trying to trick you. I think it's just they lay it out funny. So that's option D. Once we swap them around. Yeah, let's keep it rolling. We're making great time here. All right. So I think from here this crosses into the quiz 3 material. From the start up until now, the first 8 questions I think have all been from quiz 2, if I'm not mistaken. So let's keep it pushing. In this problem, they give us an increase in bacteria count over the first 3 days, and then they give us an increase of only 580 over the next additional 11 days. And they say, what's the average rate of increase over the entire period? So if there were 3 days and then there were another 11 days, we know the entire period is 14 days. And what we're going to do is find the difference from start to finish in bacteria count and then divide it by the total number of days. It's very much like finding the slope between 2 points. So if we can find the starting population count, in other words, the population count or the bacteria count at day 0, and then the bacteria count at 14, what we're doing next is basically just finding the slope between those 2 points. So what's the starting bacteria? The starting bacteria count was the 5277 that they mentioned there. And then they tell us that it increases from that to the 9569, but then it only increases by 580, up until the end. And so we have 9569 plus 580. So to get the final bacteria count, we would just add this 9569 plus 580, and that'll give us like that final bacteria count. So let's go ahead and add those together. 9569 plus 580, and we get 10,149. And then so that's like our y2, what we just found. And we're going to subtract our y1. And then basically here's the connection. This is our slope formula setup. y2 minus y1 over x2 minus x1. So now we just calculate 10,149 minus 5277, and then we divide by 14, and we get 348, and that is option C. So a huge takeaway from this one: average rate of increase or average rate of change. I'm just going to write it somewhere. Average rate of change is a fancy phrase for the slope between 2 points. Whenever they mention average rate of change, you're finding a slope between 2 points, x1, y1, x2, y2. All right, let's keep it pushing. Number 10, this is a great one. This is where you're given 3 different graphs, slightly different graphs, and you're given 3 statements, and then the kind of the catch is what they mention in this note here. So basically, for time and days, time 1 represents the end of day 1, time 2 represents the end of day 2, and so on. And so let's apply that to this one. In number 1, they say between 6 and 7 a.m. on day 18. All right, so let's stop there. Day 18, because they're talking specific times, and because they gave us this note, from time 17 to time 18. They say, time 18 represents the end of day 18, which means the duration of day 18 starts here and ends here. So this whole stretch from time 17 to time 18 is day 18. So between 6 and 7 a.m. on day 18 must be somewhere in here. 6 a.m. is how many hours into the day? 6. How many hours are in a day? 24. So dividing 6 by 24, we get 1/4 or 0.25. And so what this tells us is that 6 a.m. on day 18 should be 0.25 into the day. In other words, 6 a.m. should be at the time value 17.25. So this is 6 a.m. on day 18. All right, let's keep it pushing. What do they actually say? They say between 6 and 7, the photosynthesis rate decreased. So usually when they're talking specifics, there's usually just one graph we look to. So specifics in terms of like certain times on that one day, that's important. So 6 and 7 on day 18. We said that 6 a.m. was 17.25. And so we want to find that on this graph here, which we kind of see it, we kind of don't. It's sort of implied that it's over here. Sorry, the pen's kind of messing up. So because each of these x values or time values are 0.04 apart, so you can only assume that from here to here must be, that must give us 17.25 at the start. So you can also kind of use that to assume that this must be 7 a.m. And you could always check that by doing 7 divided by 24, and you'd likely get 0.29. So let's keep going. They said that the photosynthesis rate decreased from 6 to 7, but from 6 to 7 we can see that there's actually an increase. So this is a false statement because they said decreased and it should have been increased. Number 2. They say the rate at 9 a.m. on day 18 was lower than the yearly average rate during year 7. All right, so let's go ahead and do 9 a.m. on day 18. We're going to take 9 hours since 9 a.m. is 9 hours into the day, divide it by 24. Go ahead and get that decimal. That is 0.375, so maybe like 0.38 if they round like that. So again, day 18, we're looking back at this. And again, we got 0.38, so 17.38 represents 9 a.m. on day 18. And so that's about here. That's probably a rate of 4.5 if you look around the y value there. And they're saying that rate was lower than the yearly average rate. Anytime they say yearly average, you're looking at the yearly average graph. And they say yearly average during year 7. So year 7, I'd say that's at least 6, just about 6. So they say the rate 4.5 is less than 6 or lower than 6, and that is a true statement. All right, let's kind of get rid of some of the mess here. All right, number 3. The max photosynthesis rate in day 10 was higher than the max rate in day 9. So usually when they're comparing like max rates on one day versus another, that's where you're actually looking at this one. Of course, you're looking at this stretch versus this stretch. Again, from time 8 to time 9 is day 9, and the second half must be day 10. And so in this one, the max rates over, I guess the max rate for each day is what we're comparing. So the max rate from 8 to 9 is right here, and the max rate from 9 to 10 is way up here. And what are they saying one more time? The max rate in day 10 was higher than the max rate in day 9, which is very much true. It's much higher in day 10 than in day 9. So we have 2 and 3 should be correct. 2 and 3 correct looks like option G. And that's it. So kind of a weird problem, analyzing the graphs and stuff, but I hope that makes some sense. Let's keep it rolling on to this one. This is a great problem because you don't really need to do too much, but it looks pretty intimidating. I'm a big fan of problems like these with a lot of words where those words don't really matter, except for really this last statement here. So don't worry about these. They tell us to find the average rate of change, which if you were here a moment ago, or if you're watching this video after the fact a moment ago, we said average rate of change just means the slope between 2 points. So if they're telling us to find the average rate of change from 72 to 76, they're telling us to find the slope between 72 and 76. So to find a slope between 2 points, we identify those 2 points, and we do y2 minus y1, where cost, in this case, is representing our y values, and then divided by x2 minus x1, where the q, or the quantity in this case, is like our x values. So let's calculate 1040 minus 989. We get 51, and we divide by 76 minus 72, which is a difference of 4. So 51 over 4 is 12.75, or about 1280. And that's it. All right, let's keep it rolling. Again, another good one. Why? Because it looks pretty complicated with the function and just it seems confusing at a glance. But what do they tell us to do? They tell us to find the average rate of change between these two x values. So they're telling us to find the slope between two values. The only difference here is they're giving us the x values, so negative 0.5 and positive 0.5, and they give us the function, but they don't give us the y values. So if they give us the function, we can find the y values by plugging in these x values to that function. So what we're going to do is plug in first, we're going to plug in negative 0.5 to this function. And yeah, I'm just going to do it on my phone. 5 times 0.5 negative plus 5. So we get 2.5. I'll just write it here for the numerator. And then we're dividing by x squared plus 1. So 0.5 negative times 0.5 negative, or 0.5 squared, and then plus 1. We get 1.25. So 2.5 divided by 1.25, I believe that is 2, and that is correct. So our y value here is just a nice 2. So now that was negative 0.5. Let's plug in positive 0.5. I already know the denominator, because it had x squared, will also be 1.25. But what's the numerator? So 5 times 0.5 plus 5 gives us 7.5. So now 7.5 divided by 1.25, that is 6. So some pretty nice y values. So again, we plug those x values in to get the y values, so that now we can find the slope between these 2 points, or the average rate of change. I guess just be careful with the signs on something like this with the double negative in the denominator, but really this is just 4 over 0.5 plus 0.5, which is just 1. 4 over 1 is just 4. All right. Let's keep it rolling. So I put 2 different problems here. They're the same, problem type. Was there any difference here? No, I don't think so. So like the context of the problem is slightly different, but it's the same process. It's actually, let's talk through it. So let's talk through it with this one, and then if you want, you can try it with the other one. I'm just going to keep it rolling after this one, though, I think. So in this one, they give us a function, which is split up, which is kind of whack. So it should say q equals 1620 times 0.6 to the t. And so this is our function. They give us a function, and they say estimate the rate of change. So notice they don't say average rate of change. They just say estimate the rate of change at one specific t value. And so the approach here is to estimate a rate of change, or a slope, or a derivative at one point, at 0.5 in this case. We're going to pick a t value to the left and to the right of 0.5. So we're going to pick a t value of 0.4 and 0.6, a value to the left and to the right of 0.5. And what we want for 0.4 and 0.6 are their corresponding function values. So y values, or in this case really corresponding q values, because they give us this function q, and we're just going to plug in the t values to get y values in return. Sorry, this vent's a little loud. Give me 1 sec. I had to block that noise. All right. So what we're going to do is plug in these t values to the function, get the y values or the q values in return, and find the slope between these 2 points. And the slope between 0.4 and 0.6 will serve as a great estimate for the rate of change, or the slope right at 0.5. All right. So I will also just do this in my phone. So we're plugging in 0.4 into this function. So I'm going to do 0.6 and then x to the y, and then 0.4, and then enter, and I get this crazy decimal, and then times 1620. And we get about 1320. I'll do 0.6, just 1 decimal place. And then now I'll plug in 0.6, so I'll do 0.6 raised to the 0.6, then times 1620. And we get 1192.4, more or less. All right, so now we're just finding the slope between these 2 points. So we're doing y2 minus y1 divided by x2 minus x1. Let's give it a go. Minus 1320.6, and then we divide by the difference of 0.2, and we get negative 641. So I got negative 641-ish, and that looks like option C, and that's it. So anytime, no matter what the function is, no matter what the context is, if they're asking you to estimate a rate, or a rate of change, or an instantaneous rate of change, or a derivative or slope at one point, you will always pick an x value to the left and to the right, or t value to the left and to the right, find their corresponding y values, or function values and then find the slope between those left and right points, because the slope between the left and right points will serve as a great estimate for the slope or the rate of change at the desired point in the middle. And so, in case you want to practice with this one, there's the answer if you want to check your answer. All right, let's keep it rolling. Great problem here. I think I even have the other version. Yeah, we'll go ahead and call these 14 and 15. Same problem type, I believe, but one of them asks for the x-intercept and one asks for the y-intercept. So let's start with this one, and then we'll go to the y-intercept. So in this problem, they give us a function on a graph, and they say consider the secant line. So a secant line is a line that intersects a function at 2 or more points. Typically, the ones you'll see will just intersect at 2 points. And so, consider the secant line with the slope representing the average rate of change, in other words, just slope, in the function over the interval 1.25 to 2.75. That's the most important part, really. So 1.25, what we're going to do with that is basically put a dot on the function at 1.25 and then again at 2.75. And what they're describing when they say secant line is the line that connects these 2 points at the 2 x values they gave us. All right. So that's our secant line, what I've just drawn. And all they're asking is which choice is closest to the value of the x-intercept of this secant line. Now, it helps that I can draw a line on the iPad, and you obviously you can't do that on like a computer screen. But for one like this, where they're asking for the x-intercept, I would honestly recommend you can probably just hold up your pencil to the screen, and it's probably a fair enough estimate, as long as you can like imagine where the secant line would be intersecting at these x values, so 1.25 and 2.75. Anyway, so just from this, about 2.2 is what we're looking for, and that's option C. And another thing to point out, more times than not, the actual function's x-intercept should be very close to the x-intercept of the secant line. So that's something to keep in mind. You can kind of like use it as a guideline, I guess. Not every time, but for the most part, yeah, that will hold true. Now let's get to the fun one, where it's the same idea. There's a secant line passing through 2 points, but in this case they ask for the y-intercept. And so again, I could put these 2 points, connect the dots, and create a line. And with the iPad, I could see exactly where the y-intercept is of the secant line, but you can't draw on your computer screen. So we're just going to talk through how to do it algebraically as best we can. So the first step, again, is putting 2 points on the curve at the given x value. So at 0.25 and at 3.25. And what we're going to do with those, to go about this algebraically, is we're going to try to identify or estimate the y values on the graph that correspond to these x values. So to 0.25 and 3.25. So let's look at 0.25 here. We're zooming way in. At 0.25, we're going to estimate this y value here. I'm going to say it's like 0.25. So 0.25, 0.25, not too bad. And then we're going to zoom in over here. We're trying to get this y value corresponding to this point at 3.25. So, shoot, I don't know, maybe 1.25. That's my best bet. All right, let's give it a go. So first step, I guess second step, after we have these estimated y values, is to go and find the slope between these 2 points. So 1.25 minus 0.25, and then divided by 3.25 minus 0.25. So y2 minus y1 over x2 minus x1. Up top we get 1, on the bottom we get 3. So 1/3 is the slope of our imaginary secant line here. So now how do we use the slope to find the y-intercept? Well, if we think about the equation of a line, y equals mx plus b, we can think about what we know regarding this equation about the secant line that we are dealing with. We know that the slope is 1/3. And then we also know 2 ordered pairs. Really, we only need 1 ordered pair. So what we're going to do is plug in an x, plug in the corresponding y, and plug in the m value, x, y, and m. We're going to plug those 3 values into this equation to solve for b. Why? Because b is the y-intercept, and that's what we're looking for this secant line. So we're plugging in this x of 0.25, this y of 0.25. So the y value is 0.25. The m value is 1/3. The x value is 0.25. And then we have plus b. So we've plugged in x, y, and m into y equals mx plus b. And our goal is to solve for b, again, because b is the y-intercept. So I'm going to go ahead and calculate 1/3 of 0.25. So 1 divided by 3. Will this be posted after the live stream? Yes, it should be posted to YouTube as long as everything technically is going well. It should be posted afterwards, so you can always watch it back and whatnot. So 1/3 times 0.25, we get, so right here, we get 0.083 repeated. You're welcome. Thanks for tapping in for a little bit. I'm glad you're here because it says they're out now. It said there was 0 viewers, and now it says there's 1 viewer. Okay. Let's keep it rolling. So we have 0.083 just for this little calculation here. So now we're going to solve for b by subtracting this to the left side. So 0.25 minus 0.083. And we get 0.167 with all the decimals I had and whatnot. So 0.17, 0.16 is what we're looking for. And we do see, okay, I had to think about it for a sec. I almost chose 1.7, but it's 0.17. So 0.17, the closest thing, is option C, because 0.17 is like 0.17, and 17 is very close to 0.20, and so C is our best option. All right, I hope that made some sense. So recap with this one, we put points, dots at these x values here on the curve. We estimated their corresponding y values. I know it's very much a mess right now. So we found their y values. We found the slope between those 2 points. We got 1/3. We plugged in. We didn't need the second ordered pair. We just used 1, and we plugged in the x, y, and the m into y equals mx plus b. And once we solved for b, that gave us the y-intercept that we were looking for. So let's move on to the next one. Here's a fun one. Number 16. They say, oh, perfect. I'm glad you're here then. Glad you're watching this and getting prepared. If you have any questions, let me know. So with this one, they tell us to list ABC in order of decreasing instantaneous rate of change at these points. So basically, looking at these points on this function, we want to think about what the slope of the function is generally at points A, B, and C. So generally, we don't have to calculate a slope, but we just want to tell whether it's positive or negative. And some points might both be on a positive slope, some might both be on a negative slope, but you're also taking into account the steepness of a curve. So if a line is on a steeper slope, it'll either be, so if it's a positive slope, so let's make 2 points up, for example. So if a point is here, we'll call it x, and if a point is here, we'll call it y. These points are both on a positive slope. In other words, the function is positive both at points x and y. But x is on a much steeper slope. Not much, but x is on a steeper slope than y is. And so x would have a greater positive slope than y. Another thing to point out is y is closer to a maximum, or like where it turns around, right? And at a maximum, you actually have a slope of 0. And so that's kind of something else that plays into it, if you want to think like that. So that's why y has a lesser positive slope than x. But let's just jump into it here. So starting this problem from scratch. first, identify which points lie on a positive slope and which ones lie on a negative slope. So C is on a positive slope. A really is kind of at the top there. It's at really a zero slope, I would say. And then B is on a negative slope. So they kind of handed it to us. We are ordering these in decreasing order. So from greatest slope or most positive slope. My pen is crazy right now. It's like twitching. So most positive slope to the most negative slope. So most positive must be C because that's the only positive, and then A is about 0, and then B is our negative slope. So CAB is option F, and that's it. So most positive slope to most negative slope is the approach here, and it'll always be most positive to most negative. In other words, it'll always be decreasing order. It's kind of just how they do it, so you don't have to like look out for if they switch up on you. So I might save this one. Yeah, I'm gonna save that one to the end. I might actually move some of this junk down here and take this test out of order here. That might have shown the answer to, which I'll just cover up because no one's gonna remember that. All right, so let's jump into number 18 first, and then we'll go back to do number 17. So in this problem, they give us a function, this black curve on the graph, and they give us a bunch of colored lines, and they ask us whether the lines are like tangent lines, secant lines, or they represent average rates of change or instantaneous rates of change and all this stuff. So let's kind of just talk through each of these statements and maybe learn some stuff along the way. The slope of the so statement 1, the slope of the orange line is the slope of the tangent line at x equals 1.5. So when I see this statement, all I'm wondering is orange, the orange line, is orange a tangent line to the function at x equals 1.5? So when we look at this curve, when we look at the black curve, the original function, and we look at the orange line is skimming the surface of that black function, and so it has the tangent line behavior, so where you tangent line intersects a function only at one point, and it has this like skimming the surface behavior like it does. So really all that's left is, does it occur at 1.5? And it does. All right, so that's it for number 1. Number 2, they say the slope of the green line is the average rate of change. As we've talked about, that just means slope between 2 points. So the slope of the green line is the average rate of change between these 2 points. So 0.25 and 2.5. So really all this means is the green line a secant line? And then is that secant line intersecting the original function at 0.25 and 2.5? So whenever you see average rate of change, it's almost synonymous with secant line, or intersecting at 2 points. And so the green line is a secant line because it intersects 2 points. The question is it at 0.25? Yes. And is it at 2.5? Yes. So around 0.25 and at 2.5 it does intersect twice, and it does say average rate of change, and that is a secant line, synonym phrase, and so that is a true statement. Let's go on to number 3. All right, number 3. Slope of the blue line is the slope of the tangent line at 1.5. Okay, so that's pretty much the identical statement to number 1, except they changed orange to blue. And as we look at blue, and we identify, I guess, first whether it's a tangent line or a secant line, we see that it intersects the black curve twice. So therefore it's a secant line, and so automatically we could eliminate it because it's secant at 1.5, but also, oh my goodness, iPad is cooking. All right, so it's secant at 1.5, but also at 2.5. So had it said something similar to like number 2, where it was like secant line between 1.5 and 2.5, or average rate of change between 1.5 and 2.5, it would be a true statement. But automatically secant line and tangent line conflicts, so that is a false statement. And so we're looking at 1 and 2 to be correct, and that's it. All right, let's go back to the mamma jamma of all these problems. It's really just the most time-consuming one if you're doing it how they expect you to do it, which is how I'm going to go over it. So let's not waste any more time. I bet we can knock it out by 5 p.m. Let's do a solid hour session. All right, number 17. In this problem, they give us this population function, population in billions. So, what was I going to say? Oh, this function will always be the same exact function in all these problems. So that's kind of convenient. All right, let's jump into how I would do it. T is the number of years since 93. And then they ask about 2001 versus 2012 or 2012 versus 2001. So here's what I would do. First, I would find the T value that represents these years. So T equals something has to represent 2012, and T equals something else represents 2001. So because T is the number of years since 1993, that means that like T equals 0 represents 1993, and T equals 1 is 1994. T equals 7 is 7 years from 93, so T equals 7 represents 2000, which means T equals 8. One more year must represent 2001. I'm going to redo this. Looks just a little sloppy. Wow, I have nice handwriting when I try. That's something. All right, so now 2012, how many years is that from 1993? It's like 19. Is that right? Oh, gosh. 7 plus 12 is 19. Yeah. All right. Good night. All right, so we have our two T values. Now let's think about what they're asking. They ask us to estimate how much faster the population will be growing in 2012 than in 2001. The wording is very weird here, so what you have to think about is like first, or what we have to do is find first how fast the population is growing in this year, and then find how fast the population is growing in this year, in 2001. So you're finding the rate of change in each of these years of the population. And then you are comparing them or finding the difference in them in order to find how much faster one is than the other. So let's talk about how to find the rate of change in 1 year or for 1 year. We saw before to estimate the rate of change at one T value, you're going to pick a T value to the left and to the right of that T value. So T and P, we're going to set up a little chart. We're going to do 18, which is a T value to the left of 19, and then 20, a T value to the right of 19. And what we're going to do is find the populations that correspond to these T values. It's almost like finding the Y values that correspond to X values. We're going to find those by plugging in the T values to that function P. So I'm just going to do that in my phone, and they point out to use enough decimal places, so I would definitely recommend at least using like 5 or 6. That's not really something you can ignore, unfortunately. But here we go. So we're plugging in 18 to this function here. 1.014 raised to the 18, and then times 1.15. When I do that, I'm going to zoom in so I can write as neat as possible here. 1.477002. All right. Now we're going to plug in 20 to the same function. 1.014 raised to the 20, and then times 1.15. We get 1.518647. Lots of decimals there. It's pretty solid. And we're going to leave it at that. We're going to copy and paste this and really just do the same thing for this one. Change up the colors, make it a little more fun. And in this case, because we are finding the rate of change at t equals 8, we'll pick a value to the left and to the right in terms of the t values of 8. And we're going to find these corresponding p values to 7 and 9. So same idea. We're plugging in 7 and 9 to this function, starting with 7. We get a different color. Use this color. we get 1.267545. 754. That's, whoa, 45. Almost got it. All right, plug in a 9. Times 1.15. That will give us 1.303285. All right, that was probably the hardest part of it all. Maybe, I don't know, we're making progress. With these two ordered pairs for t equals 19, we're going to find the slope between these 2 points. Once we find the slope between 18 and 19, that will represent the slope or the rate of change or rate of growth of the population in t equals 19. In other words, it'll tell us the population growth rate in the year 2012. So we're going to find the slope between these 2 points by doing 1.518647 minus 1.477002002, and then 20 minus 18. So slope, and then I'll really just go ahead and write out this slope on the right here. Try to be efficient. Oh gosh, I can't even squeeze it in, can I? Oh gosh, 1.2675. I'll just leave it at that. You get the idea. Divided by the difference in the t values. So let's calculate each of these one by one. We're on the home stretch. 1.518647 minus 1.47702. I missed something. Yes, I did. 1.477002. There we go. Divided by 2, and we get over here on the left 0.020823 if we round. And then we're going to find the slope on the right here. So 1.303285 minus 1.2675, looking back at the chart, 45. And we get this, and then divide by 2 as well, and this will give us 0.01787. So this is the rate of change of the population in the year 2012, or in t equals 19. This is the growth rate of population growth rate in the year 2001. We're finding how much faster the population grew in, like how much faster it was growing in 2012 compared to 2001. And so all we do is subtract these two values. 0.020823 minus 0.01787, and we get 0.002953, and this is our answer in billions per year. But notice the answer choices are in millions per year. So the approach, you could probably see which one it matches, but if you want, you can always multiply this by 1,000 to give us 2.953, or 2.95 million per year. And that's it. All right. So we just worked out a solid 18 problems in about an hour while sort of explaining all of them. So this is a good reference video for this whole exam. If y'all have any questions, you can always comment or shoot me an email at carterdmath@gmail.com. And if you learned something from this video, please consider donating to my Venmo. Venmo plug. My Venmo is Carter D with 3 E's, and the last 4 digits of my number are 6910 if they ask for it in terms of like confirming identity stuff. If this helped you, please consider donating some money. I do all this stuff practically for free, so put a lot of time into this. I hope this helps. All right. I think I'll just, before the end of the video, I'll just kind of like scroll back through all the problems we worked through so you can get like a full glimpse at really all the work that was done, to show that really for a lot of them there really wasn't much work done. Really hope everyone's doing all right. Really hope everyone's not stressing this one too much. Again, if you have any questions, just hit me up. You know what I mean? Just comment on a video. Shoot me an email. This stuff hopefully is very, what's the word? Like it's, understanding this stuff is hopefully attainable. Like it's reasonable, right? Hope so. That's a pretty bad claim coming from me. I do this stuff every day, so. But again, you know, just use the resources you got. I gotta stop talking. I'll probably just say some stuff that'll just come off wrong. Alright, so I'm just gonna keep scrolling through these so you get a glimpse at everything we did today. Again, Venmo is Carter D. Alright. If you have any questions, hit me up at my email. Always happy to respond and work out any problems y'all need, and even make walkthrough videos for any questions you have. Don't hesitate to ask, but who knows, maybe if you're not asking questions, maybe that just means the videos are working just fine. They're doing what they're supposed to do. You know what I mean? Alright, I think that's all I had. Thanks so much for joining, tapping in, all that stuff. I really appreciate the support. I'll see you next time on exam review sessions for 1025. Alright, see you.